Shaowei comes from Institute of Automation, Chinese Academy of Science. He's going to give us a talk on in-hand object localization using gyro-stereo-tactile sensing. Yeah, please go ahead, Shaowei, when you are ready. Thank you.
Thanks for preferring your introduction. Good morning, good afternoon, good evening, everyone. I'm Shaowei Cui from Institute of Automation, Chinese Academy of Sciences. My research interest in focus on vision-based tactile sensors and visual tactile fusion perception for grasping and manipulation. Today, I'm very pleased to introduce you one of our recent work in hand object localization using stereo tactile sensing. So here is the background. Humans can easily inference the grasping pose of everyday objects using visual, tactile, and the experiments. This ability helps us complete complex manipulation tasks. Similarly, the in-hand object localization is critical for robots to realize fine manipulation, such as small parts assembly. Look, as shown in this figure, the robot gripper grasps its peg in random pose, and the robot needs to locate peg in the end effector and align it to the hole for assembly. In this process, visual perception is important but will be compromised in contact-rich manipulation tasks due to occlusion, distortion, etc. So in this paper, we try to address this problem by tactile sensing. This slide shows our gel stereo tactile sensing sensor. Tactile sensor. The gel stereo sensor adopts binnacular steering algorithm for surface reconstruction instead of photometric steering algorithm. This method does not require extra color normal registration calibration and reduces the requirements of light source design. The finger in the left upper part shows the contact state when finger press a notch on the surface of the sensor, and the three images are raw image and macro detection results at the tactile point cloud. As the perceived 3D tactile point cloud, the red points indicates the 3D position of each macros on the contact surface, and the macros in the contact region are shown in the yellow color. The finger in the right shows the contact states with the gel stereo sensor contacts various objects with different forces. The validation result indicates that the gel stereo sensor can measure the 3D tactile point cloud of the contact surface precisely. By the way, the yellow contact point cloud is extracted from the red ones by setting at a contact depth threshold. For example, if the perceived contact depth of the marker exceeds 0.25 millimeters, the markers will set as a contact point. Okay, here is the proposed in-hand object localization pipeline. Given this ready tactile points sensed by the gel stereo sensor, we first extract the contact points from all points by setting a contact depth threshold, named contact points detection in this pipeline. And afterwards, we initialize the grasping pose of the objects, such as the peg in this pipeline, and generates the object point cloud by sampling from its CAD model. Finally, given the yellow contact points and the blue object points, the in-hand pose can be estimated by pose set registration methods, such as ICP methods. If you have any questions about the pose set registration methods, please refer to this article for more information. Okay. Okay, in the experimental section, to verify the proposed localization pipeline by tactile sensing, we have performed small parts grasping and insertion experiments. We equipped two gel stereo sensors to our robot setup and perform real robot experiments of random grasping and inserting different small parts. Yeah. Instead of fix the peg at the end effector, we randomly place the objects in the middle of the gripper as the alignment process is completed by the proposed localization measures. We selected the four pegs at a USB interface for this experiment. Yeah. Furthermore, we also compare the finger rag measures, which is a probabilistic registration measures, with the traditional SP measures for podcast registration in our experiments. Okay, the two measures are tested on each of the peg 36 times, and the USB interface for 10 times. Okay, this figure shows a peg grasping and insertion experimental serial. The whole process can be divided into grasping, alignment, and insertion three stages. For each peg, we first obtain an initial pose for its corresponding hole, as shown in moment 3. Yeah. Therefore, the adjustment pose of the robot can be computed by the transformation between the in-head pose, the blue one. Sorry, the blue one, and its template pose is the gray one. After pose adjustment, the robot will insert the peg downwards to the hole. We choose this insertion tasks because the true value of the in-head pose is difficult to obtain. So the insertion success rate can be considered as an indirectly quantitative analysis of the localization accuracy. Note that the task assembling the turrets is less than 0.3 millimeters. So without the aid of any other model-based or learning-based assembly skills. So yeah, here's an example. Shows that a robot posts the pinch angle and roll angle and mark motions of the sensor and perceived tactile point cloud during a successful case of grasping, alignment, and inserting the USB interface. In the moment A, the USB surface pose is computed by the proposed measures. The robot then adjusts its pose and align it, finally finish this insertion. And the USB interface is successfully inserted into the base and turn on the lights. The light showing in the moment B. Okay. Okay. This slide shows the experimental results. The right table produces the assembly success rates of different pegs with two registration measures. So in the insertion results show that the finger rag based measures perform better than the traditional RASIC and ICP measures. Especially for the USB interface, the finger rag succeeded 6 times in 10 attempts, while SP only succeeded twice. Okay. We also found out that the insertion failure cases are concentrated in the case of a large pinch and roll angle, yeah, as shown in the right finger. I think this is because when the pinch or roll angle is large, the robot needs to make a larger pose adjustment due to the errors in just stereo sensor to grapes coordinate system provision. High precision insertion is easy to fail without the assistance of any other assembly models. Yeah. We further count the pose adjustment range that the proposed location matters can handle for different packs, as shown in the left table. The results show that the allowable range increases as the clearance increases, consistent with our iteration. Moreover, the pack C achieves the largest allowable range, which is caused by the irregular geometry shape of its cap. Yeah. So from this experiment results, we found that the allowable range increases as the clearance increases. Compared to the ICP algorithm, the filter rank matters is not susceptible to noise, outliers, and occlusion thanks to its probabilistic property, which is more suitable for in our case. Okay, thanks for your time. If you have any questions, please let me know by this email.